attempt to say useful things. So I'll begin with a word of prayer. So, Heavenly Father, we thank you for this day. We thank you for this semester, which is starting. Just pray that you bless this class, help these students to just do their best each day, Lord, for your glory. And I just pray that you'd give us insight this day, Lord. In your name I pray. Amen. So, excuse me. This lecture is a little bit different than some of them because I'm really just trying to hit the high points of chapter 0 and the first couple sections in chapter 1. Hopefully most of this you've seen in either Math 200 or number theory if you took it, or discrete math if you took it. There's lots of courses. You might have seen bits and pieces of what I'm about to talk about. But before I do that, I'll just take a minute to talk about what the big picture of this course is. And so, of course, this is Math 421, which we call abstract algebra. I don't know, it may have some elementary in the title, I forget. So, abstract algebra, what's abstract algebra about? Well, it's about doing algebra abstractly, pretty much. It's like that's kind of not saying anything. Fair enough. Most of this course is about what's called group theory, all right? And group theory really came into its own in the early 19th century. In particular, it came from the problem of trying to solve equations. So if you go way, way back, we've been trying to solve quadratic equations since basically there's been history, all right? Quadratic equations are pretty old. They come up in simple geometric problems. But then, about 1500s or so, we started sort of going up the ladder and trying to solve higher order things. And there were some Italians, Ferraro, Tartaglia, Cardano, these guys. They worked out the solutions to the cubic and the quartic equations. Then in the mid-18th century, Euler came along, and he realized, you know, he started seeing these things more systematically. He wrote these giant books on algebra. By then, we started to have the notation that we're still using today in terms of symbols and letters rather than writing out horrible Old English or Latin sentences expressing things. Maybe you've had math history, you know about this, but maybe not. And so by the late 18th century, it became clear that, you know, there was this game we could play to try to find like a quadratic formula or a cubic formula or quartic formula that was successful. Like, well, what's the next up the chain? Well, the fifth order formula. Like, what would be the analog of the quadratic formula for a fifth order equation, a quintic equation? And the sort of the successor, well, I don't know if he's a successor, but Lagrange at the end of the 18th century tried very hard, sort of trying to generalize the arguments and techniques which had been used to solve the quadratic and the cubic and the quartic successfully in the centuries before, and just hit a roadblock. He had this sort of systematic machine that should have been able to solve it, but it just couldn't do it. And so then in the early 19th century, it was left to the next generation to say, no, you know what, not only can't you do it, it can't be done. That's what Ruffini said in like 1813. Ruffini's like, nah, you can't do it. Now he had a proof that people don't tend to trust even now. Can't quite make sense of it. But then Abel came along in about 1821, and he proved, without a doubt, you cannot find a quadratic formula for a quintic in general. But, you know, you can sometimes prove things can't be done in sort of unconstructive ways. So proving something can't be done, that's sometimes an easier thing to do than explaining not only it can't be done, but here's why it can't be done. And that's what was left to Galois. Galois came along about 1830 or so, and he introduced a method based on looking at symmetries between the roots of equations, and he invented what's called the Galois group. And ultimately what he showed was if the Galois group of a polynomial is solvable, then there exists like a quadratic formula. And so that's where the term solvable group comes from. It actually means that the corresponding equation can be solved in the same way we can solve quadratic and cubic and quartic equations, but not necessarily a quintic equation. And so that problem of finding a formula for the zeros of a polynomial equation gave birth to group theory. Initially, it was just about permutations, which is just ways of the sort of toggling between, well, a set of permutations, a set of bijections on the set. So initially, the group theory was just about permutations of the roots of a polynomial or something like that. Most of the 19th century was like that. But then a little bit later, we had the work of Lee, Sophus Lee, and Klein, and they started seeing other uses for groups in terms of transformation groups. Symmetries of objects, like when can you say two different things have sort of the same shape or something? These are also turn out to involve what's called a group. Most of this semester we'll be studying groups, all right? I won't formally define them carefully for a little bit, but I think it's important to know, like, the genesis of why we're studying what we're studying. It goes back to classic problems of algebra and mathematics. So we've come to an understanding of what this thing is called a group, and we know a lot about it. And after monumental work by lots of mathematicians, it's been refined down to such a nice, sort of concise, clean set of ideas that we can teach it in undergraduate classes. All right? I mean, it was much messier. The invention of it was in the sea of all kinds of questions which were open-ended and difficult. But after that, there's something beautiful that came out, and that's what we share together this semester, group theory. Now, after group theory, I mean, I know the common saying around here is ring by spring, but for us, ring by about October. So we'll study rings, which is the next step up the chain. In fact, you've already been studying rings. Integers are rings. A ring is a set with two operations. It's got an addition and a multiplication. A group just has a multiplication. It has to have an identity. It has to be associative. There has to be an inverse for everything. That's pretty much it. A ring also has an addition. Polynomials form rings. Integers form rings. And then we'll study various specializations of that idea. Integral domain, unique factorization domain, Euclidean domain, principal ideal domain, all these fun things. And then ultimately the concept of a field. I won't go quite as far this semester as I went last year. I'm cutting it off a little bit shorter. And I'm saving a little bit more for like second semester. Second semester, we actually would study field extensions, generalized linear algebra, what are called modules. Modules when you take a vector space and basically replace the concept of a field with a ring. And hopefully, if things go well, if there's enough of you to do the course, there usually is these days, we might study Galois theory in that course. But Galois theory, the thing that motivated group theory is just, it's difficult. It's actually quite complicated, and it's really not appropriate for a first course, for most places anyway. Maybe somewhere in France, I don't know. But anyway, I have by now spent entirely too much time talking about these things and won't have time to cover what I wanted to cover today. But that's like every day in my class, right? So, yeah, all right. So I should charge you extra? Wait a minute. Oh, yeah. I like that. Yeah. You're going to give me money. I'll take it. In the form of books. Oh, I found that. I found it. The rest of the paddle.
I was wondering.
He got a what is it? I don't know, like a raft paddle, and it has these two plastic things you screw together to make like the paddle. And I only had one in the package, and I couldn't find the other. So I cleaned out my garage this summer, and I found this weird little plastic tube. I was like, oh, there it is. Sorry, that has nothing to do with what we're doing. Okay. All right. So you can read about sets. I'll just say this: a little bit of notation that I use that's a little bit different than the book. So just to warn you, for me, and this is a really weird place to start, but A minus B for me, this means you have A and A, such that A is not in B. Okay. So for me, that's set difference. The book and a lot of other people do this, right? Fine. All right. Let's see, what other notation should I share with you? Cartesian product of sets. All right. So what's this? Here you got A comma B, such that A is in A, B is in B. All right. Now, what's the critical feature of Cartesian products, by the way? I mean, we have what? A comma B equals to A1 comma B1. What does that give us? Yep. Elements are the same, right? Component-wise, right? So A is equal to A1 and B is equal to B1, right? I mean, whatever this Cartesian product is, that's how you do it, right? So, I mean, if you want to be picky, this isn't even in Nicholson, but did anybody ever seen this? So if I actually wanted to sort of define a substructure here, I could do it like this. You could say this is the set containing the singleton A and this guy. So you could use this set of sets to define the Cartesian product. Then that would give you the ordering that you want. It would distinguish the first entry from the second entry and give you the equality that I've written above. So this is a model for the Cartesian product. There are others. I think this is called the Kuratowski product. I found that on Wikipedia. It must be true, right? Again, this isn't even Nicholson. I don't really expect you to remember it. I just, if you're like, well, how can you do that? That's how you do it, all right? In a similar fashion, we can talk about mappings. What's a mapping? Well, alpha. You could also say function, right? So, AKA, how else can we write it? We can write A, alpha, B like that. What's A called? Domain, right? Codomain. You're like, I'm enjoying this part of the lecture. Let's just stay right here, right? So we teach you this slogan in Calculus 1. What is it? For each A in A, we assign what? A single element alpha of A and B, right? This makes alpha a function or map, right? So if you read Nicholson, he's like, well, that's okay, but it's kind of like circular because assign is really just kind of another word for function. Something like that. I mean, okay, fine. So if you a glutton for punishment and you really want to confuse the students properly, you could say, well, yeah, you could think of it this way, right? But you could also say that the function is really, it's really a subset of the Cartesian product of A and B, right? It's really a set of ordered pairs. And what's the rule? If, you know, A comma B and A comma B1 are in alpha, then what? Say again? B and B1 are equal, right? Then B equals to B1, which is just a fancy way of saying that whatever comes from A, there's just one thing coming from A, right? So this is just kind of a sneaky set theoretic way of getting this idea. So notation. And Nicholson has a few proofs using this notation, right? So if we have, if A and B is an alpha, then you can write that alpha of A is equal to B, right? Now, I do not think in this way, to be totally honest with you. I think of a function as a mapping, as an assignment, and it doesn't get me in, I mean, I don't have problems with it. But if you ask a sufficiently delicate question, this construction of what a function is in terms of set theory is useful, all right? For example, he meaningfully uses this construction to prove the following theorem for us. And this theorem is, I mean, I don't know, sometimes I give this theorem as a definition, right? If alpha from A to B and beta from A to B are maps, then alpha equals to beta if and only if what? Alpha of, I'll say x is equal to beta of x for all x in A. Now, some courses I teach, I'll say that that's the definition of equality of functions, right? But because he's given us this construction, he can meaningfully prove this theorem in terms of this here being equality of sets, right? Really subsets of a Cartesian product with B. And over here, of course, the thing we know and love, pointwise equality, right? All right, so pretty much after you prove this theorem, then you can kind of dispense with the Cartesian product set theoretic thinking of function, and you can just think about images and points. That's my, since I don't like this, that's how I view theorem 1. You guys will remember. I will remind you soon enough. Don't worry, it's happening. One-to-one maps, onto maps, the image of a map, right? These are all things we talk about. You can also talk about the composite of a map. How can we compose maps? When does it make sense? So if we have A, B, and C, and suppose we have alpha going from A to B, and we've got beta going from B to C, right? Then we can meaningfully define beta alpha, which will be a map from A to C. How do we do it? Right, we say the composite is defined to be beta of alpha of x, right, for each x in A. Mostly the thing here is, in my previous coursework with you, if you had me before, I almost always write what for this? Right, I put a little composition symbol. We probably won't do that in here, all right? I mean, I on occasion may do it, and I may even hand you some notes with that in there, but we're free to omit it if we want to, okay? So, theorem. If we have mappings, so mapping alpha, beta, gamma, then what'd I do? Did I do something? No? Okay. Oh, something I forgot to define. You guys will tell me it. Alpha composed with 1 on A is equal to alpha, and 1 on B, alpha is equal to alpha again. 2, function composition is associative. And 3, if alpha and beta are both 1 to 1 or both onto, then so is beta alpha. Now I threw some notation out there I haven't yet clarified. What's this 1 sub A mean?
Is that just identity on it?
Right. So this is Nicholson's notation. His definition is that 1 sub A is the mapping from A to A with 1 sub A of x equal to x again for all x in A. Right. So of course we're already using theorem 1, you know, that you can define things pointwise to make the definition of composition. I'm not even going to talk about this theorem 1 probably past today. We can define things about functions pointwise, right? Again, map is synonymous with function or mappings. Okay, so like, let me just prove something here. Let it not be said I didn't prove anything. Proof. So how do we prove alpha 1a phi at x? What does it give us? This is alpha of 1 sub A of x, right? By definition of composition, yep.
For part 3, do you mean that they're both 1 to 1 and onto, or one or the other?
Like, yeah, I mean,
Okay, but there's different things.
so if they're both 1 to 1, beta alpha is 1 to 1. If they're both onto, then beta alpha is onto. Yeah. If they're both bijections, then beta alpha is a bijection. Oh man, I think I did one of your homework problems. But I would like you to actually work that out. Sorry. A good question, Samuel. So the proof here, right, 1a of x is x, but that's alpha of x. This holds for each x and a, right? So therefore, alpha 1a is equal to alpha, right? In fact, the proof of all of these is pretty much the same as that. It's really not much difference to prove the associativity of functions here, is it? Right? We take gamma of beta alpha of x. What's that equal to? It's gamma of beta alpha of x, which is gamma of beta of alpha of x. But this, by definition of function composition, is gamma beta of alpha of x, which again then, by definition of function composition, is gamma beta of alpha all of x. But x is arbitrary, so that gives us 2. I think this would be considerably more difficult to prove if you tried to do it at the level of this notation. Right? Okay, so function composition. Of course, this leads us to our next favorite thing, which is inverse functions, right? So how do we define an inverse function? It's a bijection. I think that's kind of part of it. Let's see here. If alpha from A to B is a mapping, and beta from B to A is map such that beta alpha is 1a and alpha beta is 1b, right? Then what do we say? Beta is equal to alpha inverse. In other words, beta is inverse of alpha. Now the notation beta equals to alpha inverse assumes the next theorem. Theorem 4 in this section of Nicholson then proves that the inverse, if it exists, is unique, right? So this notation alpha inverse is not ambiguous. There's just a single inverse function. If there's one that exists, there's just a unique inverse. Right? But yeah, this function would also be a bijection, right? Because in order for this to make sense, you can figure out that you'd have to have that the image of alpha was in fact B, right? It'd have to be an onto map for this to make sense. In fact, that's the content of the theorem I'm about to write down, which connects these things. Let's see here. This is theorem 5. It says the following. It says if we have alpha from A to B, beta from B to C maps, all right, then we have a few things. First of all, the one mapping from A to A, the identity map on A, is invertible. What's its inverse? What's 1a inverse equal to? 1a, all right. Mr. Thomas is on the money. Let's see here. Number 2, if alpha is invertible, then so is alpha inverse. And what is the inverse of the inverse? It's the function again, right? 3, if alpha and beta both invertible, then beta alpha invertible, and what do we say? Beta alpha inverse is equal to alpha inverse, beta inverse. This is the sock shoes identity for function inversion. All right. And now the theorem I was advertising a second ago when I was talking about what is needed for a function. I mean, the obvious question to ask here is, so when is a function invertible, right? When's a map invertible? And this theorem kind of puts a nice sort of, it's a nice completing thought there on that question, a nice summary. A map alpha from A to B is invertible, all right, if and only if both alpha, I'm an idiot. Alpha is both, the order of words matters, doesn't it? If alpha is both 1, 2, 1 and onto. The proof is on page 15. I would encourage you to read it carefully. All right. These are the sort of things we should have beat to death in Math 200. It may or may not have happened for you. So if it hasn't happened already, you really do need to read these initial sections carefully. All right, so this is actually very interesting already. There's a, comment I should make here. If S is a set, right? Then we can say perm S will be alpha from S to S such that alpha a bijection. All right? So we can define the permutations on a set. Set of invertible mappings on the set. All right? Like shuffling a deck of cards, permutation of the cards. And if you take the theorems that I've stated here and proved like a tiny part of, what they say then is that in this set of permutations, there's an identity, 1 sub s, right? It says that everything in here, every bijection has an inverse, right? If alpha is in permutations, and alpha inverse is in the permutations. And also, if they're both 1 to 1 and onto, then the composite is also both 1 to 1. In other words, if you take two bijections and you compose them, you get another bijection, right? And also, the composition of bijections is associative, right? So as we'll carefully define eventually, that means that the set of permutations forms a group under function composition. So that's what we're doing right now, by the way. So I'm trying to develop some of the background briefly, and then we'll get into group theory proper. Last year I started with the definition and group and went from there. But I think it's healthy for us to spend a couple of lectures just building up examples. So at the moment, I'm just trying to remind you things we know about compositions of functions and inverses and stuff. And this will be nice, because later in the course, if you ask yourself the question like, is the composition of bijections a bijection? Be like, oh yes it is. That's theorem such and such in section blah of Nicholson. Game over, end of story, all right? So this right now, we're settling what you may say is sort of the set theory of the problem. These we haven't really introduced extra structure. This is all just about Cartesian products and mappings at the moment. All right, so next section is on equivalences. Yep.
Are there any non-intuitive side effects if we...
These are non-intuitive side effects? Go on.
If we remove the non-empty qualifier?
That's what I was just going to ask you. It seems like you could just define, if it's empty, you could just define perm of S to be the set of just the identity function, right?
Seems harmless enough.
Is there a function from the set to its set?
Yeah, I think the only function is the identity function.
Probably goes back to the, I don't know, if you want to. I only care about the non-empty ones, though. Samuel is always making these kinds of non-trivial, trivial comments. Let's see here. All right, I digress. Okay, so actually, let me not do a bunch of writing. Let me just talk about this with you guys. You guys know what an equivalence relation is, right? What is an equivalence relation? Who has never seen an equivalence relation in any of their coursework before? All right, let me go on then. No, I'm just kidding. Okay, fine. So an equivalence relation, I need to erase something. Yes, how about this? Equivalence relations are very important, and they, I think, really are at the heart. Students not understanding equivalence relations is probably one of the more difficult stumbling blocks to overcome in this course, all right? So it's good to kind of settle the basics of equivalence relations in section 0.4, especially if you're rusty. But here's this notation. A equals B means, and here again it's one of these sort of set theoretic construction things. A comma B is an element of the equivalence relation equals, which is a subset of A cross B. So this is the set theoretic mumbo jumbo, set theory, yoga, I don't know, whatever you want to call it, of equivalence relations. You can view it technically as a subset of the Cartesian product of A and B. A and B? A and A? Come on, dude. Sorry, notes got me. And this has to have three things, right? What are the three things you have to have? Reflexive, right? A is equivalent to A. Also, if X is equivalent to Y, that implies what? Y is equivalent to X, so this is called symmetric, right? Reflexive, symmetric, and then what's the third one? X equivalent to Y and Y equivalent to Z implies X is equivalent to Z, right? So reflexive, symmetric, and transitive. Now, you're like, isn't that just equality? You know? Like, what's the difference between this and equality? Well, what's that?
Aren't they equivalent?
Aren't they equivalent? Well, equality is an example of an equivalence relation, but certainly not every equivalence relation is equality. Although that's a little bit of a lie. It's a question of interpretation. I mean, you could say every equivalence relation is an equality of sets. It's just not an equality of elements. So in particular, we have this definition. Oh, come on. Dead to me. I'm out of practice. So A, this will be X in A, such that what? Such that X is equivalent to A, right? This is the equivalence class generated by A. And this theorem that we have here in Nicholson tells us some very important basic facts about equivalence classes. Here's the theorem. Number one, A is an element of the equivalence class of A. How do you get that? Yeah, that's the reflexive property, isn't it? The equivalence class of A is equal to the equivalence class of B if and only if A is equivalent to B. All right? So you can prove that. This is equality of sets, right? So you have to prove double containment. That's the content of the proof here. You suppose you got an element of this one and you show it's in there and vice versa. That involves the symmetry as well as number one. Number three, if A is an element of the equivalence class containing B, then A is equivalent to B. It's a little bit different. It's kind of a combination of the first and second one, really. And then four is very exciting. If A is not equal to B, well, the equivalence class of A is not equal to the equivalence class of B, then the equivalence class of A intersection, as in set theoretic intersection, is equal to the empty set. Proof is on page 18. If I had better planning skills, we had time for it today, but I blathered on about uninteresting history, so forgive me. So this sets the stage for what? What do we do with equivalence relations? Why are they so neat? What are examples? You gave me equality as an example of equivalence relation. What else is an example of equivalence relation? What's that? Oh, modulus. Yes, that's what we're talking about next time. Modular Z mod n, right? This is equivalence classes relative to the modulus by n. Say two things are equivalent if their difference is a multiple of n. It's a good equivalence relation that we spend the whole next lecture talking about, right? Yeah. There are many examples. I mean, he has a few more. Let's see here. Another nice geometric examples. You could look at, let's see here, like lines in the plane with parallel lines, right? Like you could say two lines are equivalent if they have the same slope. And then the equivalence classes would be the set of parallel lines with a given slope.
Is that quotient space?
What's that? Yeah, then the question is what's the next thing would be the quotient space. So A sub this, which he calls the quotient set, this is equal to, it's a set of sets. So this is the so-called quotient set. And he explains that if we look at phi going from A to the quotient set defined by phi of A equal to what? The equivalence class generated by A, then this mapping I just wrote is the so-called natural map. Natural map. And he then argues that, in fact, this shows you that well, there's another page of material I haven't talked about, but it's okay, we still have 10 minutes. Let's see here. Let me back it up for a second here. So all of this, what this means is if you look at A, right? Say this is a picture of A, right? Then we can sort of just, so here's like A1, A2, A3, right? A4, however many you got, A5, there could be, there could be lots of these, right? I mean, there doesn't have to be a finite number. There could be an infinite number of equivalence classes, whatever. The point is, if you pick any point in the set, right, there is an equivalence class which contains the point. Because, number one, A is in the equivalence class generated by A. So you can do that for any point. So every point in the set A is covered by an equivalence class, right? And also, they're mutually disjoint, right? So the intersection of these lines should be like dotted, right? I don't know how to do it, but each point in the set is contained in just one equivalence class, right? So Nicholson calls these equivalence classes cells, right? And this is an example of what's called a partition of A. So given an equivalence relation, we obtain a natural partition of the set into equivalence classes. And vice versa. If somebody gave you a partition of a set that is, a collection of subsets of the set whose union cover the whole set and which are pairwise disjoint, then that partition would allow you to create an equivalence relation. How would you create the equivalence relation from the partition?
You said it would be called in
He says you say they're equal if they're in the same set. I'm going to take that and replace it with you say the 2 points are equivalent if they're in the same cell. But yes, that's the idea. So these are interchangeable ideas, equivalence relation and partition. And one of the equivalence relations he defines, and one of the examples he gives, example 3, is the so-called kernel equivalence. He says for a mapping, you can define an equivalence relation on the domain in terms of the kernel equivalence. So his example 3 is, he says x is equivalent to y if phi of x is equal to phi of y. He calls this the kernel equivalence. I sometimes call this the fiber equivalence because that says that x and y are in the same inverse image of some singleton in the codomain. In other words, you can take the domain and you can divide it into these fibers. So this would be like the inverse of a singleton. Let's say this is B, whatever. So if you have 2 points on a fiber, it means that phi of x and phi of y, they're both equal to B. They both map to B. So this kernel equivalence is what I sometimes call the fiber equivalence. And he kind of makes this ultimate point, which is that any partition can be seen as arising from the kernel equivalence of some map. Now, I know it's a lot to sort of take in this section, but you should read it carefully because it sets the stage for what's called the first isomorphism theorem later in the course, which the heart of is set theory. It's this kernel equivalence and so forth. Now, I've assigned you a homework problem or two, which will help this to sink in more. I know I haven't said enough for you to really understand it if you haven't thought about these things deeply before. All right? Now, time. Always time. All right. Well, I guess that's chapter 0, so that's kind of a good place to stop. Next time, I will talk about integers and hopefully modular arithmetic. I start to have some notes I can post on that I've written myself. I'm still in the bubble whether or not I should ask you to read them or not. You can look at them. They're last year's notes. I don't know. They may or may not be helpful. At some point, they'll be helpful. Maybe not yet. Thanks, Tori.